All right, let's take a look at the warm-up. All right, starting once again with higher order differential equations. And the idea is this one should be relatively quick to go through. You want to get into that flow of writing out your auxiliary equation and moving from there. So in this case, remember our general assumption is that our solution looks like e to the RT. We plug that in to generate our auxiliary equation, which looks something like that. We might try to factor that thing. If we can't, we'll have to use the quadratic formula, where we'll see our solutions are going to be, let's see, if we use minus b plus or minus the square root of b squared minus 4ac, so 4 times 2, which is 8, all over 2a. It looks like this one simplifies to negative 1 plus or minus I. So we see we have complex roots. And then we have a specific solution form associated with those complex roots. We take those and we would write out our general solution, which would look like what? What would our general solution look like in this case? E to the negative t times c1 cosine of that coefficient times t plus c2 sine of t. There's our general solution form. Now the reason we're starting with this is just to once again summarize what we did for the complex case. The idea is that's my solution form. If I were to take that thing and just distribute that leading coefficient, I could write it like this. And I write it like this because I want you to see the two linearly independent solutions. Remember, our general form is some constant x1 plus some constant x2. This would be one solution. That would be another solution. There's two of them. They're linearly independent. That should form our general solution. Now, where do we get the solution form from? Why can't we just take our assumption and plug in our complex values? Well, in some sense, we could. We could say our solution was e to the negative 1, maybe I'll grab a positive value, plus I times t. And it is a valid solution. We just didn't like it because it has those complex values in there. Right? And it's not really useful to us if we're trying to analyze a specific system. We want real values. But what we could do is distribute that t and then use the property of exponents to rewrite it like this. And then if we recall that we have Euler's identity, which says e to the I theta is cosine of theta plus I sine of theta. That's one of those identities you just have to commit to memory, right? It's the Pythag of college, right? You just got to know this one. But if we apply that to the second piece, we have e to the negative t times cosine of theta plus I sine of theta. And if I really want to stress thing, I can actually distribute that first term if I really want to kind of hammer this point home. And the point is that if we just plug this thing in and get our solution looks like that and compare it to our other solution, it basically looks like we took this guy and we said, okay, the real part of that result is a valid solution. The imaginary part is also a valid solution. And they're linearly independent, so I could really just use those to form my general solution. So instead of memorizing the solution form, I could just plug in the complex value, right? And then separate the real and imaginary parts and use each of those as one of the solutions. Questions about that? That's the big kind of generalization. The big idea is I can use the real part as one solution, the imaginary part as the other solution. All right, that was the big idea as we extended into systems. So what we talked about last time was now I have this system of differential equations. And our first step to solving the system would be to calculate the eigenvalues and eigenvectors. And I have done that ahead of time here. And these are eigenvalues. I'm going to calculate the associated eigenvectors. question topic 4 of our general solution. We're going to follow that same model we just talked through. I'm just going to plug in complex values. And I'm going to do some algebra, some vector algebra, so that I can see the real part and the imaginary part. I'm going to use each one of those as my linearly independent solution. So remember that my assumption was that my solutions look like some eigenvector e to some eigenvalue t. And I'm just going to grab one of these and grab one of these. So I'm going to write this as some eigenvector. I'm going to choose the positive one. E to the some eigenvalue. I'm going to choose the positive one. And then just like before, I'm going to write this as 2 plus I. I'm going to write this as e to the negative t times e to the 2t times I. Just like I did in the other case. And then just like the other case, I'm going to use Euler's identity now to rewrite that e to the 2ti. And so all that's really just the same. That's what I want to stress here. This isn't some new complicated process. It's the same process. The challenging part comes now, though. Right, before, we could clearly see what the real and imaginary parts were at this step. Now it's more complicated. So now I have to kind of blow this whole thing up so I can really see what the real part is and what the imaginary part is. So I'm going to bring my e to the negative t out front. And then I basically need to times this vector by this scalar function. So I need to take the first component, this 2 plus I, times all of this stuff. So I'm going to take 2 times all that stuff plus I times all that stuff. So I'm going to take 2 times the cosine of 2t plus 2 times the times I sine of 2t plus I times all that stuff plus I times cosine of 2t plus I times I sine of 2t. But what is I times I? Negative 1. So this is basically minus sine of 2t. Okay. That's just 2 plus I times all that junk. And I take 1 times all that junk. That's much easier. I got cosine of 2t plus I sine of 2t. Okay. Once again, the goal is just to separate the real stuff from the imaginary stuff. So e to the negative t. I'll put my real stuff first. 2 cosine of 2t minus sine of 2t. Right, all my real stuff in boxes maybe. And then my imaginary stuff, my complex piece here, but they both have I, so I'm going to factor that I up. I times, so I got 2 sine of 2t, and I got a plus cosine of 2t. And the second component's pretty much already separated. Okay. There, now I can see the real piece and the imaginary piece. If I want, I could take the extra step of like breaking this into 2 vectors. I really wanted to, but I don't need to, I don't think. I can see the real and the imaginary parts from here. And so the idea is that my general solution is just some constant times the first solution, some constant times the second solution. And the big idea is that my real part will work as one solution. So I can take C1 times e to the negative t, 2 cosine of 2t minus sine of 2t, and then cosine of 2t in the second component. The real part works as one solution. And then the imaginary part Works as another solution. I don't need the I, remember, I'm just taking the imaginary part. I don't need to bring the I with me. It's the coefficient of the I. So I have 2 sine of 2t plus cosine of 2t and sine of 2t. Once again, I'm kind of a fan of memorize as little as possible. It's the process that's kind of important here. And it's the same process that we saw for higher order. Any questions? Yep. So the big the big idea is that I can take just the real part as one solution and just the imaginary part as one solution, separate pieces, right? So kind of for the real reason of why I can do that, there's a proof I can show, right? I'll give you the kind of the quick version. I'll give you the quick version in this case because the algebra will come out a little bit cleaner. Okay. Here's why, right? I got this solution. That was one solution here. One solution really should be e to the negative t cosine of theta plus I e to the negative t sine of theta. That's really supposed to be one solution. I used one eigenvalue to get this, and really I should use the other eigenvalue to get another solution. I could do that, and what I would find out is that if I plug that stuff in, the other eigenvector will be the conjugate of the first eigenvector. These are two solutions. Now, these two solutions are linearly independent, so I can use these two to form the general solution. Constant times the first one plus constant times the second one, that should be the general solution. But all I need is any two linearly independent solutions to form that general solution. I don't have to use these two. Let's see if I can find some other ones to use instead. Right? How do I find another solution? Well, I could just multiply these by constants and add them together. Right? If I take 2 to the first one minus 4 to the second one, that should be a new solution. Right? So watch what happens when I take 1/2 of the first one. If I take 1/2 of the first one, I would get this plus 1/2 of the second one. If I add those together, these cancel out. And I'm left with just 1 e to the t cosine of theta. Okay, that must be a solution all by itself, right? I can choose different constants and so what I can do is say, why use that complicated solution when I know that I could choose the right constants just to give you the real part and just to give you the imaginary part. They're both linearly independent. Let's use those instead. Okay? That's kind of a why. Other questions? So we go through that process, and from that on, we say, oh, okay, grab the real part, grab the imaginary part. And that's what we did here. I just grab the real part, grab the imaginary part. All right, other questions? All right, I got some administrative stuff here. All right, I tried some of this stuff. I'm going to get it in range. We will have a sample exam. It will be Thursday at final. I know. I did want to address some of the concerns about that. One of the concerns for sure is, what about partial credit, right? I don't like taking all or nothing, multiple choice exam. I will get that partial credit. So I want to explain how it will kind of work so that maybe it alleviates some of those concerns. The partial credit is going to be there. It's just going to be in the question writing. So you're not going to get a whole bunch of questions like, solve the differential equation, go. A, B, C, or D, what's the right answer? Here the questions look like, given the differential equation x double prime plus 2x prime plus 2x equals 0, which of the following is the correct auxiliary equation? That is the partial credit. Normally you do something like this, you get 2 points for that auxiliary equation, you get 2 points for something else. I just built into the question style. Another question might be, given this system of equations, if these are the eigenvalues and these are the eigenvectors, which of the following is the correct solution for it? Right? So you're only having to do one part of those problems. Right? Or here's a system, what are just the eigenvalues? Which of the following eigenvalues? Okay. So you kind of get that partial credit the way the questions are written. Okay. All right. Any other concerns about the exam? I will send out some practice exams, but it will be different. It will be not standard. right now I got somewhere between 20 and 30, but I haven't timed myself out yet. So that comes out to be short. I'll add more. I try to go 3 or 4 times. So I should be able to finish it in about a quarter of the time allowed. So we're a 2-hour exam. If I can't finish in a half hour, it's probably too long. So I tend to try to time that by. There's always a balance, right? I don't want to make it long so you rush on time. So I can make it nice and short, like 10 questions. Then you got 10 questions and you miss one, that's 10 points, right? So there's always a balance between those two things. Other questions? All right. Other notes, the Learning Center will be open during exam week, Monday through Sunday, 6 p.m. to 9 p.m. So be aware of that if you want to do some last minute studying. I posted an extra credit one, another one. So there's only 2, unfortunately. I wanted to get more, but that's all I got. It's like a lab-ish assignment. So it will talk about visualizing these systems and doing eigenvalue, eigenvector calculations. So it should kind of help you study as well. But it is extra credit, so you're not required to do it. And then today we want to focus on repeated roots. Right? We've done regular distinct roots. We've done complex. Now repeated roots. So that's what we got on the agenda. All right, repeated roots. So I got this system of differential equations. I want to solve the system. First step, calculate the eigenvalues and eigenvectors. But I don't really have to do a lot of work for that because what are the eigenvalues of this system? 1, 1, and 2, because for a diagonal or an upper triangular or lower triangular matrix, the eigenvalues are just going to be those diagonal entries. All right, so I know right away, just by looking at this thing, these are my eigenvalues. Okay. All right. Now, remember, my goal is to form some general solution. And this is a 3x3 system, so my general solution is going to look like this. Okay. And to form that, I need 3 linearly independent solutions. And I got a bunch of theorems from linear algebra that kind of help me along this way. I know, for instance, that eigenvectors from distinct eigenvalues are linearly independent. So this guy is going to give me an eigenvector. This guy is going to give me at least one eigenvector. They're going to be linearly independent. That gives me at least 2 solutions. The problem is that I'm not guaranteed to get 2 linearly independent eigenvectors from that one eigenvalue. So I'm not sure what's going to happen here. Right? All right, so let's just start here. Let's get the easy one first, right? If lambda equals 2, then I got to solve a minus lambda I times my eigenvector equals 0. A minus lambda I is basically cutting off the diagonals. That's the matrix I get. Remember, this is really times the vector x1, x2, x3 equal to 0. Right? But I don't write that stuff because I'm augmenting with 0 and basically comes out to reducing this thing anyway. And actually, I've chosen this one, so there's not really any row reduction to do either. And so I can just go ahead and write out the equations represented by this system. First row would give me what for an equation? Negative x1 equals 0. Next one's negative x2 equals 0. What's going on with x3? It is a free variable. Okay. So that means my eigenvector is going to look like 0, 0, and this can be any number. If I want, I can write a parameter there, and then I can factor out the parameter, and that would be my eigenvector, or really I could just choose some number for t. Right? Both are very good options here. Basically, my eigenvector is 0, 0, 1. And if you wrote 0, 0, 1 seventh, that would also be correct, but that would be annoying, right? So don't do that. Okay? But any multiple of this eigenvector should also be an eigenvector. All right, to the next one. If lambda equals 1, All right, so this gets 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. What does this mean? All right, well, I basically only have one equation here. That equation is the last one. It tells me x3 is equal to 0. What's going on with x2? It's free. What's going on with x1? It's free. Okay? And so this is a little bit trickier. I can't just choose some values here. I really should identify these as parameters. I'm going to call x1 s. I'm going to call x2 t. My eigenvector would then become s, t, and 0. Okay? Or any values of s and t. Now, what I'd actually like to do, though, is write this in terms of the s's in terms of the t's. So I'm going to rewrite this. And from linear algebra, you might remember this is parametric vector form. I'm going to write it like this. S times 1, 0, 0 plus t times 0, 1, 0. And you can kind of check to make sure that's equivalent, right? If I take t times this vector, I get 0, t, 0. If I take s times the other one, I get s, 0, 0. If I add them together, I'm going to get s, t, 0. Okay? But when I write it like this, I can see that this represents all the possible eigenvectors, right? All the eigenvectors are a linear combination of these two vectors, 1, 0, 0, and 0, 1, 0. Which means those two vectors are a basis for this eigenspace, right? I'm basically two eigenvectors here that are linearly independent, and they're a basis for this eigenspace. And so that's great because basically I got this solution here. This solution was u1, and I can just pair up the eigenvector with e to its eigenvalue. But now, because I plugged in my eigenvalue and I basically generated two eigenvectors, I could say, well, let's use this eigenvector. And then I could write a solution like this, e to the 1 times t. But I could also get another solution that looks like this. Are those two solutions linearly independent? They are. Right? And so I can use this one to be my second solution. I could use this one to be my third solution. I'm all done. That's it. Right? General solution is just putting them all together. Any questions? The only really kind of tricky part there is the linear algebra stuff, right? Being able to separate the vector into two pieces and deal with your free variables and all that kind of stuff. Any questions? Yes, repeated eigenvalues is easy, right? All right, so obviously there's a problem here. We don't always generate two eigenvectors from that one eigenvalue. If you do, then you're basically done. What about this one, though? Same process, eigenvalues, eigenvectors. What are my eigenvalues here? 1, 1, 2. I think I said last time that you won't have any 3x3 systems. I think I'm going to need to have some 3x3 systems to really test this point. Okay. So what I'll say is that if you have 3x3 system, the eigenvalues are going to be kind of nice, like this. So make sure if it's upper triangular or diagonal, you can pull out the eigenvalues like that. Right? I don't want you to have to calculate hard determinants of 3x3 systems. But if I gave you this system, you shouldn't have to calculate any 3x3 determinant, right? You should be able to just grab the eigenvalues. Okay. All right, so I got my eigenvalues. The only ones I'm really concerned about is lambda equals 1, right? I know that I'll plug in lambda equals 2, I'll get some eigenvector, that's going to be what it's going to be. What about lambda equals 1? So let's do that one first. Because actually in the earlier class, I did lambda equals 2 first, and it kind of screwed up my notation all the way through, and it really was kind of confusing. And so I told them that tough luck, the next class we'll get the good notation. All right, so if lambda equals 1, we plug this in. We basically subtract 1 by diagonal, I get 0, 1, 0, 0, 0, 0, 0, 0, 1. What are the equations I generate? Looks like I get x2 equals 0. I get x3 equals 0. What's going on with x1? It's free. That means I've got this eigenvector that is any number and then 0 and 0. I'm going to call it 1, 0, 0. That's my eigenvector. But I'm not happy, right? I only generated one eigenvector. I didn't generate a second eigenvector. I need to get 2, right? I'm going to get some sort of solution from this guy. It's going to look like whatever that eigenvector is, e to the 2t. Now I got 1 here. I got maybe my first solution, which is going to be 1, 0, 0, e to the t. But I don't have my second solution from this eigenvalue. So how do I find what's going to be u2? Right? To do that, I basically need to calculate some other eigenvector. Okay. So what I'm going to do now is I'm going to calculate a generalized eigenvector. I basically plugged in my eigenvalue. I didn't get enough regular eigenvectors. So what I now have to do now is generate a generalized eigenvector. How do I do that? Well, here is my eigenvector equation. That is the equation I use to generate eigenvectors. An equation I could use to calculate the first generalized eigenvector, which I'll call x2, is this equation. Okay. So basically, I solved the first one to get my eigenvector. I got to have at least one. I have a theorem that says I'll get at least one eigenvector for the eigenvalue. But if that's all I get, I can use this equation to get a second one, because now I know what x1 is. Plug in x1 where it's supposed to be, find x2. Okay. But this thing could be repeated more times. Like, this is all I need to do, because I just need the second eigenvector. But I could have something where lambda equals 1 is repeated 10 times. In which case, I'm going to need a whole bunch of extra generalized eigenvectors. And so I could keep going, actually. And if I needed a third eigenvector, I could use the second eigenvector to calculate the third eigenvector. And you can kind of get the pattern here. I could generate a fourth from the third, and so on and so forth. Okay. Now we just need the second one, so let's go ahead and calculate that. I need to do this. I need a minus lambda I times x2 is equal to my x1. Okay. A minus lambda I, I've already calculated that. That's just this guy. Times x2, well, that's just some kind of generic three-dimensional vector. But now it's not equal to 0 anymore. Now it's equal to x1, which is this vector. So this is the system I'm trying to solve, not with zeros on the right-hand side, the other vector over there. I solve that just by writing my little augmented matrix if I want in general. This one we kind of don't need to, but the difference here is that I really have to include that right-hand side. Before I just kind of ignored it because it was all zeros. I can't ignore it anymore. At this point, I would do my row reduction, but I chose a system that's pretty nice, so you really don't have any row reduction to do. So I'm just going to write out my equations now. My equations are going to be x2 equals 1 and x3 equals 0. What's going on with x1? It is free. But I got to be a little bit careful here, right? So what is x2? Well, x3 is fixed at 0, x2 is fixed at 1, and x1 is free. Now, just like before, I could really choose a value to put in here. I could say, well, x1 equal 1. There you go. There's your x2. There is your before I said that's one of them, you can use a whole bunch of other ones as well. So I use 2, 2, 0 generalized eigenvector. multiply this vector by 2, eigenvector 2, 2 is 0. Right? So the generalized eigenvector, you can't just multiply this to get a new generalized eigenvector. I could choose any other number I want for that first piece. I could have 1, 1, 0, 2, 1, 0, 4, 1, 0. Any of those are acceptable, right? But I can only change that free variable. Okay? So be a little bit careful there. You can't just scale that guy. Any questions there? There's some linear algebra stuff there. Really, I can't scale this guy, but I can add any multiple of my original vector, right? This is an affine space, not a vector space. Okay, but I got my eigenvector here, right? So, whoa, I got my second eigenvector. I couldn't get 2 from the first eigenvalue. I generated the second guy, but we actually just can't plug this into the same solution form. There's also a special solution form that are associated with these eigenvectors. Okay. When I calculate that first eigenvector, I am guaranteed to get my first solution. It looked like this. Okay. And I already formed that guy. He's right there. But now, if my second solution is based on this generalized eigenvector, it's going to look a little different. It's going to look like this plus that. That's what my second solution would look like. And right now you guys are going, multiply by t thing. Right, we're doing the multiply by t thing again. Not 100% here, right? This is actually a little bit different. If I looked at the third solution, if I needed a third eigenvector, I use this equation to generate the third generalized eigenvector, that third solution would look like this. x3 e to the lambda t, x2 t e to the lambda t, x1 t squared over 2 e to the lambda t. Okay. And actually, as we extend this higher, we're going to generate some factorials in that denominator. And it's going to end up looking more Taylor series-ish than just multiplying through by t. Okay. Now, for our case, we just need this guy. Right? So this was our generalized eigenvector. That means my solution here, my second solution would look like, 1, 1, 0, my generalized eigenvector, e to the lambda t, plus my original eigenvector, t e to the lambda t. So now I've generated both solutions from this repeated eigenvalue. All right, any questions so far? Yep. So these are just individual solutions, right? My general solution is constant times u1, constant times u2, constant times u3, right? So I have to take that whole u2 and multiply by a constant. I'm done. All right, I'm going to talk about a little bit of vocab here, and then we'll just form the general solution here. Okay, this guy was repeated twice. Right? Lambda equals 1 and 1. Right? Now we're talking about the multiplicity of that lambda. The algebraic multiplicity is how many times it's repeated. Here is repeated twice. Algebraic multiplicity is 2. If it was repeated 10 times, algebraic multiplicity would be 10. Okay? Now, there's also something called the geometric multiplicity. And that's basically related to the number of eigenvectors you generate when you use that eigenvalue. So in this specific case, I have an algebraic multiplicity of 2, but a geometric multiplicity of 1. And that disconnect is why I had to calculate the generalized eigenvalue. In the first case we did, I had an algebraic multiplicity of 2 and a geometric multiplicity of 2. And all was right with the world, and just form my solution. Because when there's this disconnect, there's a problem. That disconnect, we say the matrix that generated that is a defective matrix. We didn't like the fact that it didn't give us those eigenvectors. We called it broken, right? Defective matrix. Okay. So in this case, I got my second solution. I only need one more, but I still haven't used my last eigenvalue, so I'm going to use that real quick. If lambda equals 2, let's plug that guy in. I would get -1, 1, 0, 0, -1, 0, and 0, 0, 0. Is that right? Yep. I actually can row reduce this a little bit. I'm just going to add the two rows together, create a new first row. So this is what it would look like if I row reduced it. The equations I'm generating here are -x1 equals 0, -x2 equals 0, x3 is free. And so this third eigenvector, or my third eigenvalue, would be 0, 0, and let's say 1. Which means my third solution here is going to be 0, 0, 1, e to the 2t. So I got that guy, I got this guy, and I got that guy. And then the general solution, the final product here, is some constant times the first solution plus some constant times the second full solution plus some constant times the third solution. Any questions? So what I did in my first class, well, I did this calculation first to get out of the way. And so that generated my first solution, U1. But then when I was talking about the generalized eigenvectors, U1 here wasn't U1 anymore. U1 was U2. And I got a little wonky, right? So cleaned everything up. See, isn't it much better to be in the second class? Okay, notation for the book is a little different, not really. So this is how the book will describe it when they're talking about that generalized chain of the chain of generalized eigenvalues and vectors, right? So that's not exactly what we wrote, but that's not exactly how we calculate our first eigenvector, right? But if I subtract that guy to the other side, and then I factor out the x, that's what I get. And if I just did the same with all these other ones, I would get the same thing. So they just didn't do the algebra ahead of time. I prefer this because this is how you actually calculate them, right? You're going to generate that guy and row reduce it. Okay. So this will be in the book, Theorem 97. And then lastly, from the book as well, there's what the solution forms look like. And so I did want to just show that kind of generalization as the extend higher. Those factorials are generated in the denominators here. Okay. And then I want to really disappoint you here. They're hard. And when you're dealing with these effective matrices, these effective systems, it's really hard to analyze these things. And so this process we just went through about finding a generalized eigenvector, that actually only works for a pretty small group of systems. Right? In general, we have an algebraic multiplicity of k, or let's say 10. Right? That will work to be a 10 times. Right? This process works if when we plug in that eigenvalue, we get one eigenvector. Actually, exactly one. Right, so if we have repeated k times, we only generate one eigenvector. This is the problem in the process of handling that type of defective matrix. If you want to repeat it 10 times, we plug in the eigenvalue once, and you generate two eigenvectors. That is a whole separate problem. That is a whole separate process to generalize that. Okay? Now, there are ways you step up from one to the next, but it really involves a lot of advanced linear algebra. This basic system, that you call the matrix system, or what it's related to, will be the Jordan canonical form of a matrix. So it really requires kind of a lot of extended linear algebra just to generalize this. So you might say, well, why are we even wasting our time if it's such a small subset? Well, the idea is that most of the systems we're going to work with are going to be 2x2 systems. It's a very common size system for us to work with. If you're doing a kind of physical or engineering system, or really dealing with forces, those are the types of systems that are generated there. For a 2x2 system, if you have a repeated root, it has to be in a situation where you can solve with a generalized eigenvalue. So it works for that pretty big group of problems. Okay? It's just hard to extend past that. I'm sure I just preemptively answered a lot of questions there, right? You're probably like, wait a second, does this work for all of these cases? I mean, I can just see people writing that question down, so nailed that one, right? All right, any questions? Okay, the last topic is going to be geometric stuff, all right? A little bit of geometric and a little bit of Mathematica. The idea so far, we have systems that look like this. And if A is a 2x2 system, let's throw some weird numbers in here. 1, 2, 3, 4. Then we're going to solve this thing. And our solution forms are kind of locked in now, whether we get distinct, repeated, or complex roots. In the distinct case, we get solutions that look like this. C1, making stuff up here, e to the 4t, C2, negative 1, 1, e to the negative 2t, right? They have this form, right, as their general form. Something like this, okay? But this u here, this vector function, we think of as u1t and u2t if it's being generated from a system of equations. I mean, we could clean up this other side to really write it as one big vector form. Like if we had some initial conditions, we could figure out what C1 and C2 are. And so you might get something like, C1 might be 2, and then you'd have 2e to the 4t plus 3e to the negative 2t, right? And then 0 minus 3e to the negative 2t. You get some values, and you can represent your solution in this kind of vector form. Okay. When you want to think about how your solution is changing, what values is it returning, you might say, well, what is the value of my function at time equals 1? Well, if you plug that in here, what are you going to get? You're going to get a vector with some number here and some number here. Right? And you can certainly think of that as some location on a coordinate system. Whether you think about that as the point or the vector that goes to the point, I really don't care. But it's identifying some spot in a two-dimensional space. And at some other time, you would have some different number. Maybe over here. And so for a 2x2 system, we can view this solution as really a set of what? Set of equations that we put in some value for the parameter and we get outputted a coordinate, right? It's really a set of parametric equations. And so we can actually plot our solutions using parametric plots and actually view these as space curves. All right, real quick, we'll just kind of go through a couple things you can do. The extra credit is basically kind of what I'm going to talk through real quick here in the last couple minutes and just kind of give you an idea of what I'm going to do here. All right, so I got some matrix. I have no idea if this is a useful matrix or not. I just made it up. Then I define my vector u to be a vector whose components are u1 and u2. And I want it to be kind of a function here because I want to evaluate and do things with it. Now, one thing we've done already is if I run this guy, I can certainly calculate my eigensystem, and I can use that to kind of verify my work for my homework. That seems really ugly. Let's make this a little bit nicer. That's not very nice at all. That shouldn't be right. There we go. That's better. Okay. So I can certainly do that. And then I could use my knowledge of differential equations to form what my general solution looks like, knowing what the eigenvalues and eigenvectors are. But I could actually use dsolve directly. I could use dsolve, and because I've defined my vector u here, I could write u prime of t is equal to a, and matrix multiplication is done with a dot, and say u of t. And then just like any other dsolve command, I have to say what my dependent variable is, my independent variable. And so I should be able to do that and get my solution, right? And then just like we already used dsolve before, I can also do all the fancy stuff to extract solutions. I can also use initial conditions. So for instance, an initial condition might look like what? It might look like u of 0 equals 1, 2. So I can kind of type this in just like I would kind of type it in regular math notation, right? I'm just putting in that vector definition there. And sure enough, it's found my constants here. Now I have a list of lists, and I always hate that, so I'm going to pull out the first element of that. It just gets rid of a list of curly brackets. Not a big deal there. But the other fancy thing I like to do with dsolve is kind of extract the solutions. And so before, you might have done something like x of t gets replaced by that guy. Well, I'm just using u here, so I can actually do that same thing. It's going to pull out each of those pieces, and then I can actually store it to some definition, solution. And now I can really figure out what my solution is at time 1. And I probably want to see some decimal values. So that's what it would be like at time 2. And so you can really see that I am getting these point values as I put in different time values. And then if I wanted to see what they all look like, I could certainly parametric plot these guys over some range of t values. And of course, I'd want to organize that and scale that as well. So I can really see what my solution curves look like. But that's only for one specific initial condition. I don't really like that. So when I was dealing with first order differential equations, and I wanted a view that would kind of show me all the solutions, regardless of the initial condition, what did I have to do then? What did I use to graphically view all those solutions? Vector plot. I can do the same thing here. I can really just use vector plot and type in a dot, and this time I'm just going to put x, y, and let x go from, say, -1 to 1, because my scaling will be kind of ugly otherwise, pretty sure. And I'll get something that looks like this. And I can adjust the scaling as I want here. And what we're going to talk about a little bit at the beginning of class next time is that depending on the solution form, I will be able to see what that looks like for this vector field, because I can see some of the eigenvectors here, right? So for instance, my eigenvectors were 1, 0. I really see a straight line solution here pointing in the direction of over 1 up 0. I can see that eigenvector. The other eigenvector is 1, 8. It's over 1 up 8. And I can kind of maybe see a straight line solution that would be somewhere in this range. Hard to see with the scaling, but it's there. And if we look at the general form, we can see why that is. I'll show you one more case real quick. If I just put a 1 here and a 3 here, I should get complex values. If the eigenvectors are complex, I really don't know what they're going to look like here, and I will see that because I won't see straight line vector solutions. I'll see this rotation. So we'll see the repeated rows, I'll see one vector solution and the others. For the skinny rows, I'll clearly see two eigenvectors. And for complex rows, I'll get a swirling pattern. We'll talk about it a little bit at the beginning of class next time, and then we'll start reviewing for the final. If you haven't yet, I have exam 1 and exam 2. If you haven't picked yours up, I brought them to class today, and they are over there.